chapter 23. All right. Now, for chapter 23, we are going to introduce a new physical quantity called electric potential. And also, we will talk about the relation to electric potential energy and also to other aspects that we did talk about in chapter 21 and 22. Then the first thing here, we are going to learn how to calculate the electric potential energy of a collection of charges. Then you might have 2 charges, 3 charges, like an infinite number of charges, and you're gonna find what is really their total potential energy. The meaning and significance of electric potential. Okay, this is a very important physical quantity. How to calculate the electric potential that a collection of charges produces at a point in space. Okay, then also we are going to find and how it is really related to Coulomb's law. We're going also to understand how to use equipotential services to visualize how the electric potential varies in space and their collection to electric field lines. How to use electric potential to calculate the electric field, okay, and the relation, of course, between the two. Now here, one of the applications is the one type of welding here. Electric charges flows between the welding tool and the metal pieces that are to be joined. You can see that in the picture. And this produces a glowing arc whose high temperature fuses the pieces together and make them melt, because that material, it's able to be melting and connecting things together. The tool must be held close to the metal pieces in order to maximize the electric field. And this is how we get to understand what is really relation between the voltage, which is, we call it the electric potential, and the electric field. Therefore, you're going to see that the electric potential energy is really an integral part of our technological society. Now let's look here at this picture here. We have here parallel plates. One of them is positive, one of them is negative. And then the direction of the electric field, it is from positive to negative. And therefore, if you have a positive test charge, like Q0 here, is gonna face, or like is gonna have a force acting on it downward because of the electric field. As the charge moves downward from point A to point B, where like point A, it is near the positive charge, to B, where it is the negative charge, the work done by the field is actually independent of the path the particle takes. Now, we are going to understand the idea of potential. It's very, I would say, similar to the gravitational potential energy. Whenever we have a field and we have a conservative force, we are going to have a potential energy function related to it. Now, if here the positive charge moves in the direction of the field, then the field does positive work on the charge and the potential energy decreases. Because remember, it is all final minus initial. Now, if the positive charge moves in the opposite direction, then the field does negative work on the charge and the potential energy increases. Now, if the negative charge moves in the direction of the field does negative work on the charge, and the potential, yeah, okay, like here, or, yeah. If that, now we are talking about, if the negative charge, now here talking about not positive, negative, electric moves in the direction of the field does negative work on the charge, and therefore the potential energy increases. It's opposite. And if the negative charge moves opposite to the direction, then the field does positive work on it, and the potential energy decreases. Now, I will say here, if we have two two, let's say, what I was going to say, yeah, 2-point charges, and we we want to, like, if you look at the picture here, this is Q, the source of, and Q0 here, it is the test charge. And we can say here the work done by the electric field of 1-point charge on another does not depend on the path taken. If I will do from A to B, it's going to be the same from A to another point. Therefore, the electric potential energy only depends on the distance between the charges. And this is, as I said, it is because of the nature of the electric force. Okay, the electric force, it's a conservative force, and therefore its work does not depend on the path, like we discussed this in Physics 201. Now, this equation here, it is calculated, it is used to calculate the electric potential energy of 2-point charges. And here I will say this is really Q and Q0, two charges, and the distance between them is R. Then I will say this is how we calculate U. We can say U electric to differentiate it. I like to maybe to use K Q Q0 over R, or later we will know that it's maybe more convenient to put it like a Q0, and then this is K Q over R. And that is more convenient because it is relating the electric potential energy with the electric potential. Okay, then here I will say the electric potential is different from electrical potential energy. Now, of course, potential energy is actually, it has units, of course, of joules, like any other energy. And it is defined to be zero when the charges are really very far from each other, which means like they don't feel the effect of each other. The equation here also, it is valid whatever the sign of the charges is. Now here we have two charges that they have the same sign. The interaction is repulsion, and the electric potential energy is positive. Like if you can see here, this is really the relation that we did, like here. It's like if we will put different values for R, and as we can see here, U always is positive, and as R goes to 0, U goes to infinity, and as R goes to infinity, U goes to 0. Now here, if the two charges have opposite signs, the interaction is attractive, and the electric potential energy is negative. And also we have here the same conditions. Now, what is really good about the electric potential is that it is a scalar quantity. Therefore, if you wish to calculate what is the total electric potential for a distribution of charges, just what you need to do is you need to add, like in mathematics. Then here, if I have charges Q1, Q2, Q3, and I will say the potential energy associated with Q0 depends on the other charges and their distances from Q0. This is for the electric potential energy, but the electrical potential energy is the algebraic sum of all the for each. Here, U, it is Q0 over 4 pi epsilon 0, Q1 over R1 plus Q2 over R3. And we can, have it, written like this. And as I said, maybe always I like to have it easier like this, nice looking. Now, potential, it is the electric potential, it is potential energy per unit charge. Then, which means here, if I will use UE is going to be Q0 times V. Okay, we use for the electric potential V. And the potential of A with respect to B, it is VAB, it is VA minus VB, and that is equals to the work done by the electric force when a unit charge moves from A to B. Now, this is a source of electric potential, which is a battery where we have positive and negative, and the difference between the two terminals is 1.5 volts. This is the dry cells that we are using all the time. The electric potential is due to a single point charge. It is, we call that V equals 1 over 4 pi epsilon naught Q over R, or as I said, V, it is K Q over R. Okay, where R, it is really the distance between the charge and the point that you wish to calculate the electric potential. Like electric field, potential is independent of the test charge that we use to define it. And for a collection of point charges, just you're gonna add, and we can say also here that V total is K, and that is really here QI over RI from I equals 1 to whatever number of charges I have. Now, there is a strong relationship between the electric potential and the electric field. Then I will say if you move in the direction of the electric field, the electric potential decreases. But if you move opposite to the field, the potential increases, like we introduced this at the beginning. And I will say moving with the direction of the electric field means I am moving in the direction of decrease in V and vice versa. And if we are going to move slowly a unit charge, which means it has 1 coulomb against the electric field, we must apply an external force, and that the amount of that external force per unit charge equal and opposite to the electric force per unit charge, which is the electric field. And therefore, we can create here a relationship between the electric potential and the electric field. Then VAB, which is VA minus VB, equal negative, because it's opposite, like the change is opposite, from B to A E dot dl, where the unit of the electric field here can be expressed as volts per meter instead of newtons per coulomb, but of course these two units are really equivalent. Now the electron volt, we can actually introduce a new units for I would say energy, that they are really more convenient than the joule, and one of them is the electron volt, and that is the electron volt equals 1.602 10 to the negative 19 joules. This is the electronic charge, the charge of the electron. And then this is how we convert between joules and electron volts. Also, when a particle with a charge Q moves from a point where the potential is VB to a point where the potential is VA, the change in the potential energy, it is UA minus UB equals QVA minus VB. Electron volts and cancer radiotherapy. One way to destroy a cancerous tumor is to aim high energy electrons directly at it. Each electron has a kinetic energy of 20 million electron volts, very energetic. And 1 million electron volts, of course, it is 10 to the 6 electron volts, and transfers its energy to the tumor through collisions with the tumor's atoms. Electrons in this energy range can penetrate only a few centimeters into a patient, which makes them useful for treating superficial tumors, such as those in the skin or lips. Actually, this morning there was an announcement that in Australia they have something, a breakout, something like a new for treating cancerous cells. All right, I'm gonna stop here so that I will make my videos short. Thank you, and I will see you in a little bit.